this is a set but in the form of a sequence.
Yes, sir.
This set contains elements of the form 1 over n, where n is from the set of natural numbers. What is the supremum of this set?
1.
Because the
Yes, sir.
maximum element would be 1
1,
and the infimum of this set is
0.
0. Does this supremum belong to this set or not?
Yes.
Yes.
Supremum is 1 and this set is basically this 1, 1 upon 2, 1 upon 3 and so on. So the supremum is 1 which belongs to the set. Infimum would be 0 but it is
Doesn't
Does not
not part of the set. So we call that this set has a maximum value 1 but this set has no minimum value because the least element is 0 but it is not part of the set.
Yes, sir.
But it has infimum as well as supremum. Okay, so number 2, B set is the set sin n where n belongs to the set of natural numbers. What is supremum of B?
1.
Because sin n takes
Yes, sir.
maximum value to be 1
1.
and infimum of this set is
Minus 1.
minus 1. They belong to the set.
Yes.
Yes.
So, yes.
Yes, natural numbers belong to it.
Yes or no?
Yes.
Minus 1. Minus 1 does not belong.
Give me value of n such that sin n becomes plus 1 or minus 1. You know very well sin 90 degree is 1.
Yes, sir, 90.
So the value of n to be 90, subject to the condition that I am taking n to be in degrees.
G.
Yes,
But
sir.
usually this n is taken into radian. When you see some sort of sin n, then n is in radian. When you see sin x, x is in radian. So I think there would be no any n in radian such that sin n becomes 1. But it will converge to 1. It may not be possible. Okay, it means I want to ask you that I have this n in radian, whatever it is, and this n becomes equal to 90 degrees for what value of n? 1 radian equals 90, 2 radian, 3 radian, it will always be in points.
Yes, sir.
It will never be whole radian into 90 degrees, so it's not possible. Because n takes only whole number
Whole
values,
numbers.
1, 2, 3 and so on.
Yes, sir.
So we have different examples. I can take any crazy set and we can always discuss what is going to be the infimum of that set and what is going to be the supremum of that set. The next set I am going to take is minus 1 power n. N belongs to the set of natural numbers. But I can take it in some other words. Okay, this is okay. What's going to be the supremum?
1.
Supremum of C set is 1 because the maximum value would be 1 and infimum of C set is minus 1 and I think both belong to
C.
set C. So if a supremum belongs to your set, it's going to be the maximum value of your set. If infimum belongs to the set, then it's going to be the minimum value of your set. Okay. There are some notes or remarks. If a set A is not bounded above, if a set is not bounded above, then what is the supremum of that set? If your set is not bounded from above, then what's going to be the supremum of your set?
Not unique. Not
Yes.
infinite.
It's going to be positive infinity.
Yes, sir.
Like, example, I give you a set. Let's say the set is 1, 2, 3 and so on. The set is not bounded from above.
Yes, sir.
It means it goes on
Infinity.
forever. So the supremum of this set is going to be plus infinity. Similarly, if a set is not bounded from below, so I'm not writing number 2, it will take time. Not bounded
Below.
from below, then supremum of, sorry, not supremum, infimum of, let's say that set is B, is going to be minus infinity. Not bounded from below, minus infinity infimum. And what about supremum of this set? We don't know. If a set is not bounded from above, supremum of that is plus infinity. What is infimum?
Don't know.
We can't say.
Yes.
But if we are given in a specific example, then we can say, okay, this is infimum
Infimum.
and this is supremum. The third remark, we call this the second remark.
Second.
The third remark is, and the fourth remark are a bit more important. These are the things that will help you in MCQ. So try to keep these things in your mind.
Yes, sir.
What is going to be the supremum of a null set and infimum of a null set? You know very well phi stands for null set.
Wow.
No any. No any.
Phi is a set with no element.
Please give us time. Please give us time.
Yes.
Zero.
Zero means, what is the supremum of this set?
Positive infinite.
Positive infinity.
Supremum of a null set is, supremum is negative infinity. How is that possible? The elements of your set are always less than or equal to supremum. You know very well. Elements of your set. But if you have no element, then what's going to be the supremum? You say that the supremum is going to be minus infinity. It is sometimes used in notations. Maybe this thing has no clear idea, but when you solve some sort of problems involving supremum and infimum, then this thing might help. So maybe if you are unable to get the picture of this, okay, why this happens, then okay, it's not a problem. You just keep this thing in your mind. But supremum of a null set, it means all the elements are null set are less than minus infinity. But since it has no any elements, so we are okay with minus infinity. Supremum is minus infinity. It means the set of upper bounds for null set is
Nothing.
whole real line.
G.
Set of upper bounds.
G.
2 is upper bound for null set.
G.
Yes, sir.
3 is upper bound.
G.
Minus 2 is upper bound. Minus 3. So least of
G.
those all upper bounds is minus infinity.
Infinity. Okay.
And infimum would be
Positive infinite.
positive infinity.
I was thinking about the real line.
Yes. So this is a good example. So minus infinity to infinity is the set of upper bounds as well as lower bounds for a null set.
G.
So what is the least element? Minus
Yes,
infinity.
infinity.
What is the greatest element? Plus
Wow.
infinity.
Wow.
This is something good. Okay, so next thing that we want to discuss is what we call the Cauchy sequences. But the question arises that why we are not okay with convergent sequences. Why it is sometimes very much difficult to deal convergent sequences. Then we are interested to discuss Cauchy sequences. Because in convergent sequences, if you are given a sequence an, you are interested in its limits. This A is to be the limit of a sequence, and we call this sequence to be convergent sequence. But it is not always possible to find that limit. Not because when we discuss series, we discuss basically the sequence of partial sums. So to study series, we must know sequences.
Sequence, yes, sir.
We'll come to that later on, but it is difficult to find the limit. That's why, without going into convergent sequences, we discuss another, the weaker structure, what we call the Cauchy sequences. So what is the main idea behind that? What were convergent sequences? You had a limit A and you had some terms of your sequence. After some time capital N, the distance between terms of your sequence and your limit is going to be smaller than the radius of this, what we call epsilon. This is the definition of convergent sequences. But what do we mean by Cauchy sequences? That after some interval, you don't know this limit A. You don't know whether A exists or not. But the difference between any terms of your sequences is going to be the less than given epsilon. So you don't know limit, but you say that okay, after some time, the distance between any two terms of your sequence is going to be smaller and smaller and smaller. So we call these sequences to be Cauchy sequences. What is the definition? So AM is one term of a sequence, AN is another term, their distance is less than epsilon. And what is epsilon? For all epsilon positive, there exists capital N from the set of natural numbers such that whenever you take some M and N after this capital N, this thing happens. This is what we call Cauchy sequences. Let me give you a good example. I am taking a sequence with first term 3, 3.1, 3.14, 3.1428, not 1428, 141, 3.1415, 3.14157, up and so on. This is a sequence. We always study in the beginning classes that a sequence is a set of numbers which are generated by a fixed rule.
Definite rule.
Definite rule, but that definite rule is not necessary.
Achha.
Definite rule is it's a function.
It's a function.
How you define a function? You define a function with a rule, or you define a function with just a mapping. And mapping should satisfy some properties, okay?
Yeah.
For each element in set A, there exists a unique element
Yeah.
from set B, that's a function. And definite rule for a function is not necessary. So, we claim this is a sequence. What is the rule for the sequence? We don't know, but this is a sequence.
So it is a mapping.
Sequence is correspondence.
Sequence.
First element is 3, second element is 3.1, third element is this, fourth element is this. So, there is a mapping between set of natural numbers and this set, so hence we call this set to be a sequence.
Wow.
The question is, what is the limit? Difficult to find, simply. Very much difficult. And let me tell you the limit for the sequence is.
Why?
It's a sequence, and no rule is necessary for a sequence. A sequence is mapping between natural to some other set, we know very well that thing. And I claim the limit of the sequence is pi. And we know very well pi is a number we always use in our primary classes. But leave this thing, because it is very much difficult to find out the limit of the sequence. That's why we are not interested in convergent sequences. Because always it is not possible to find the limit.
Yes, sir.
So we are interested in Cauchy sequences. What are Cauchy sequences? You always check the difference between two terms. If this difference becomes very, very small as possible, we call these sequences to be Cauchy sequences.
Wow.
And you see what is the difference between these two?
0.1?
0.1. These two?
0.003.
This minus this? 0.04.
Yes.
This difference
Zero.
0.001.
Yes, sir. 0, 0.
This term minus this term. Everyone knows subtraction. This minus this.
Point
0,
0,
0,
0,
0, 0.
0.0005.
5, yes, sir.
Okay. Does this difference become smaller and smaller and smaller? So when you go ahead in this sequence, the difference between any two terms, any two means not consecutive. You take 1000th term and then you take 10,000th term. Let's say the difference between those two terms will be as small as you want. We call this sequence to be, or these type of sequences to be
Cauchy
sequences. And the thing is that this number is a rational number. This number is a rational number. This number is a rational number. And this is a sequence in the set of rational numbers. And this sequence is Cauchy. This sequence is?
Cauchy.
What is the limit?
Irrational.
Limit is not rational.
Yes, sir.
This
It
is
means from when you are interested to go from Cauchy sequences to convergent sequences, you introduce a new set. That set is set of real numbers. This is another reason why we are interested in set of real numbers.
Real number, yes, sir.
So there are different reasons we discussed in the beginning. So Cauchy sequences are very good and basically when compared to convergent sequences. We are mainly interested in these sequences, not convergent sequences. So we claim one thing, that if a sequence is Cauchy sequence, it implies
it is convergent.
it's convergent sequence. Is it okay?
Always.
Not always.
But okay, one is convergent, that is the Cauchy.
This is okay.
Okay. Converse is true.
This sequence is convergent
Yes.
to pi. This is always a Cauchy sequence. So if a sequence is convergent,
Then
obviously it would be a
Cauchy
Cauchy sequence. But what about the converse?
every Cauchy sequence is convergent. Not possible. Yes, this is the Cauchy sequence.
When you talk about convergence, you always talk about your limiting set. In which space do you lie? I lie in set of rational numbers. In the set of rational numbers,
It is convergent.
every convergent sequence is Cauchy,
Cauchy.
but every Cauchy sequence is not convergent in the set of rational. Because this is a Cauchy sequence, this converges to pi, which is not rational. So we say that this sequence is not convergent in
That
Q. But if you take set of real numbers, then every convergent sequence is Cauchy, every Cauchy sequence is convergent. The reverse is true in the set of
Real.
real.
So what is about rational form? Every Cauchy is not convergent.
Every convergent is Cauchy, but every Cauchy need not to be convergent in the set of rational numbers. But when you take the set of real numbers, then both sides are true. Every Cauchy sequence is convergent, every convergent sequence is Cauchy. I think this is good example to illustrate this idea that what do we mean by Cauchy sequences, what do we mean by convergent sequences. You can give this example to anyone with having good understanding of pi, because pi is irrational, but this sequence is Cauchy. Okay, let us go to something else. Is this rational or not?
Rational?
Rational?
Sure. What is n?
1 upon n.
What is n?
When I say n, it's natural.
Okay, then it is also rational.
Rational. You know very well, a number is rational.
When
This
it
number
is
is rational. What is your sum?
it is also rational.
Rational.
Yes, sir.
If you give it a rational power,
It will become rational again.
Again rational.
G. Take limit.
but What happens when you take this limit?
This become a rational.
E.
This become a rational. Wow.
We have done this thing, everyone has done this thing in intermediate. This is a theorem I think we use every time. But this, everything is rational, but when you apply a limit, you get something that is
Irrational.
irrational. So this is the same idea. You have a rational number. So for n is equal to 1, you put n is equal to 1, you get something that is rational. Not 3, but something that is rational.
Okay.
You get n is equal to 2, you get something that's rational. You put n is equal to 3, you get something that is rational. So every term is rational, but the limit is,
Rational.
this limit is pi, but this limit is.
E.
Same. Irrational.
So you have this sequence, which is a Cauchy sequence. It converges to something that is E,
E.
but this does not converge in Q, this converges in
Ah.
R.
Or.
This is a Cauchy sequence.
G.
It is not convergent into Q, but it is convergent
In R.
in R.
R.
G.
It is convergent.
G.
But when you talk about convergence,
G.
you always ask a question, what is the limit?
G.
What is the limit? Okay, the limit is E. Does it lie in Q?
No.
It does not lie in Q. So you say that this sequence is not convergent in Q.
G.
But you say this is convergent in R.
G.
R. Yes, sir.
But the question is why this thing is convergent. This is the question. So, do you have any result previously we have discussed so far that claims that this thing is convergent? Because up to now, we have discussed convergent sequences.
G.
It means I give you any sequence, you tell me whether it is convergent or not. Okay, you can apply basic results, you can apply a sandwich theorem, you can apply some related results to find out the convergence or divergence of sequences. If I ask you, what about the convergence of this sequence?
Again, 1 upon n and 1 upon n.
Yes, you always break down the things.
G.
You only know this thing.
Limit.
You only know basics that, okay, this thing is convergent to 0
0.
and this thing divergent to, let's say, positive infinity, and this thing is oscillatory, oscillates between
Minus
positive
1
1 and
and
negative 1.
G.
So you use basic results to deduce something. Now how can you deduce this thing that whether this is convergent or divergent? When I said theorems on limits, there were some list of theorems, but we didn't mention. You can break this down into two. N goes to infinity, 1 upon n times 1 upon n, and you can apply a limit on both these separately. This limit would be 0, this limit would be 0, so
This becomes 0. G.
you can always do this thing. You can't say directly, okay, this happens. 1 upon infinity is infinity, so 1 upon infinity 0, this doesn't happen.
Yes, sir.
One thing we should always keep in our mind when we study real analysis, this thing is not defined.
Yes, sir.
0 times infinity, everyone else says it is 0, but it is not defined. Infinity minus infinity not defined.
Are these not indeterminate forms?
These are indeterminate forms. These are not defined in the case of real analysis. But when it comes to measure theory, we define these things by certain notions.
We can't say every Cauchy is convergent
Every Cauchy is convergent, but in the set of real numbers.
in the set of real numbers.
Real numbers, not in Q.
Not in Q, yes, sir.
Every Cauchy is convergent, every convergent is Cauchy is R. But if you talk about other sets like Q, then every convergent is Cauchy, but every Cauchy is not convergent. So let me relate this thing. These are the people who passed with 55% along with 45% policy. Can you relate the thing?
G.
These are those people who have got marks more than 55. They are also passed with 45% policy of JST and PST.
Yes, sir.
Okay,
G.
but these are the people who are only passed with 55 plus.
55.
So they are not actually Holding both large.
Yes.
Something is missing.
So if a person is from this set,
Then.
it is always from this set. If a person is in this set,
It's
then
not always from this.
may or may not be here.
Yeah.
May or may not be here. So you can relate these things. So you can call this thing to be 55 and
Yes,
45% policy.
Yes, sir.
This is only 55 pass.
55 paths.
So you know very well most of the people are with this case,
Yes, sir.
who are passed with only 55, but they do not lie in 45% policy.
Policy.
There are people who lie in 45% policy, there are very few. Who are passed in this case, they are also in pass.
Yes,
That
sir.
case?
That case.
But if they are passed in that case, they may or may not be passed in this case. So this is the thing to relate. So if you write this thing, you can remember this thing easily.
Yes, sir.
What is a monotone sequence?
Either
Either
increasing
increasing or either decreasing.
Whose terms are not decreasing or not increasing.
Monotone is the sequence is going on in the same order.
Yes, sir. Whose terms
Increasing
are
Simply
decreasing.
increasing.
Decreasing.
decreasing or decreasing. Yes, sir.
We call increasing to be monotone, increasing, decreasing to be monotone, decreasing. What is strictly monotone sequence?
A retrans
Always.
is greater than other part. In the case of
The
increasing,
second term must be greater than the first term. N plus 1 is greater than An.
so equality doesn't hold there.
Yes.
Equality doesn't hold. You have this monotone sequence. Monotone increasing or decreasing?
Increasing.
Decreasing.
Increasing. And strictly
G strictly. Not strictly.
it's monotone.
G.
It's monotone increasing as well as decreasing,
Decreasing.
but not strict.
Yeah.
Not strict. What about this?
Increasing, but not
It's
strictly.
monotone increasing,
But not strictly.
but not strictly.
Yeah.
Because sometimes these are equal,
Yes,
Yeah.
sir.
sometimes the next one is greater.
Yeah.
Monotone increasing, the property is this: an plus 1 is greater than or equal to n. An plus 1 means the next term.
Next term is
If it is greater than or equal to n, then we call it monotone
decreasing.
increasing.
Yes, sir.
And an plus 1 is less than or equal to n, we call it monotone
Decreasing.
decreasing, and this is monotone
Increasing.
increasing.
Yes, sir.
We use this monotonicity to define or to illustrate a convergence criteria. We call it monotone convergence criterion. It means there is a criteria which tells you that whether a sequence will converge or not. It depends upon the monotonicity of the sequence. This is what we call the monotone convergence criterion. And we have these monotone convergence theorems in so many subjects, in functional, in measure as well. Lebesgue dominated convergence theorem and so on and so forth.
Even for the integration of a function monotonicity.
Monotonicity, I think in what we call Riemann-Stieltjes integration. Not in Riemann, but Riemann-Stieltjes. When we substitute something,
Monotonicity is
yes,
important.
it's there. Okay, I have a sequence that's monotonically increasing. It means what happens? N plus 1 is greater than or equal to n. I have a sequence that is monotonically increasing. And it's bounded from above. So you call this thing to be a theorem. I have a sequence with two conditions. It increases monotonically, and the second condition is it's bounded from above. Then what happens? Then An is convergent. So this is a very good criteria criteria to check that whether a sequence converges or not. You have to check two things. The sequence is monotonically increasing. It means the sequence increases,
Yes, sir.
but it is bounded from above. It means it increases, but it has some bound.
Yes, sir.
Then it is a convergent sequence. And I think we can define another theorem as well by just reversing the conditions. If a sequence is monotonically decreasing and bounded from below,
Below.
then it's also convergent.
Convergent.
So this is a good criteria to check that whether some sequences are convergent or not.
Bounded from above means like
It means all the elements in your sequence will be less than or equal to some fixed value. Then it is convergent. We are not talking about what is the limit. We are saying it is convergent. That's all. We are okay with this. It is not necessary to find out limit every time. Just you need to tell that whether it is convergent or not. Because I told you if the sequence is convergent, it would be a Cauchy sequence. And we are interested in Cauchy
Yes,
sequences
sir.
mostly. We are taking the same sequence. You have to check two conditions, whether it is monotonically increasing or not, whether it is bounded from above or not. Is it monotonically increasing?
for sure.
Yes, it is increasing.
Decreasing.
Put n is equal to 1. 1, 1, 1, 1.
Third square root
It
is.
would be 2.
Yes, sir.
Put n is equal to 2.
2.
3 by 2. 3 by 2 square would be?
9.4.
Is 9 upon 4 greater than 2?
Yes.
Obviously.
Yes, sir.
So this sequence increases or is monotonically increasing?
Increasing.
You can't check in this way. There is a definite way I am going to tell you, but this is just a small criteria. And it is bounded from above. You can check boundedness as well. Just you open this by using binomial theorem, and you can see that this whole sequence would be bounded by 3, a number 3. It means all the terms in your sequence will be less than or equal to 3. All the terms in your sequence. So this sequence is monotonically increasing. It is bounded by above, hence it is convergent. What is the limit? We are not interested. Later on we can find out the limit of this sequence is named as E, what we call Euler. And you know very well, this converges to E as n goes to infinity and E is 2.718 and so on. But what we are interested in, whether this converges or not. How to check? Just take two criteria. It should be monotonically increasing, it should be bounded from above. Both things can be checked easily. How to check something is monotonically increasing? Check this thing.
Terms.
Can I reformulate this thing taking n down?
Yes, sir.
N plus 1 divided by n is greater than or equal to 1. When this thing happens, take n plus 1. It means in this sequence, replace n by n plus 1. Take n, divide them, answer should be greater than or equal to 1. It is monotonically increasing. This has nothing to do with ratio test or something like that. This has nothing to do with that. You might have done ratios test, root test, obese test and so on. But this has no relationship with that. Somehow it is, but not here.
One is there, n plus 1 is there.
Yes.
But this is also the form of increasing.
Yes.
Yes.
Just I have written this in another form. This and this are same. When this thing happens, it is monotonically increasing. When this thing happens, it is monotonically decreasing. You can check these things easily, and there is a lengthy proof of this. If we start the proof, it will take half an hour, so we are not going for that.
Yes.
We should discuss something else. I will share these notes with you in PDF after scanning, and I will tell you the resource from where I have taken these things.
Yes.
These things are a bit concise.